Uh, Hello everyone, Kazi here. I wanted to share a delightful problem with you. So here is the statement of the problem. Okay? So imagine you have a ring of radius r, and then inside of that you have a rod, or let's say a stick of length L. Now if you imagine that the stick sort of undergoes small oscillations inside of this uh, circular ring of radius r, the question is to find what is the angular frequency of this angular frequency of this small oscillation. Right. So actually off the top of your head, at least one observation that you can keep at the back of your head is that whatever solution we obtain, we expect that the limit as L goes to 0, meaning that this stick kind of becomes like a point particle. So basically you had let's say the stick with something like this with the length L, and then as you keep decreasing the length, it starts becoming closer and closer to that of a point particle here, right? So now basically if you want to study the small oscillations of a point particle, we know that this basically this scenario of a point particle inside of a ring is equivalent to that of a pendulum of radius r. So in this case you expect that omega to be equals to square root of g by r. So basically what I can write down is that in the limit, this is something to check after we have gotten our answer, is that the limit as L goes to 0, omega should go to square root of g by r. This is a sanity check, right? So how do we actually approach the actual problem at hand, right? How do we go ahead and solve it, right? So let us actually first make a couple of observations. Let us imagine this is my circular ring. Oops. Let us imagine this is my circular ring, and say this was the equilibrium position, this is the radius, this is the center C, and the whole ring has a diameter of 2r, right? So this is the center of mass. Basically if we draw a line that goes through the center of mass, since the center of mass is bisecting this uniform rod, we expect it to be perpendicular when we drop a line from the center of the sphere, right? Now if you imagine, if I imagine, let's say, displacing this slightly, then what will happen is there's going to be a normal force here. There's going to be a normal force. There's going to be a normal force here, and then there's going to be a normal force here. Now, can we say something about the nature of these normal forces? Yes, we can. It should actually pass through the center of this, center of the ring. The reason being that normal forces are actually perpendicular to the surface, right? So if you draw a tangent, the normal force must be tangent to that point. The normal force must be perpendicular to the tangent at that point. And there's a theorem in geometry which says that if you have a tangent and if you draw a perpendicular from it, it must pass through the center of the circle. So basically these two normal forces actually pass through the center of the sphere, right? Now as the rod moves inside of this constrained ring, the center of mass is also going to move, right? So you're going to have another perpendicular here. If I draw the perpendicular here, just because it's bisecting, we'll have a perpendicular here, right? Now because the length of the stick is going to remain constant, I can imagine tracing this around the entire ring, right? In that case, notice how this, since this is perpendicular, is going to be perpendicular to the center of mass at every point. This gives you a sense that the center of mass itself must be moving in a circle, where this stick is kind of the line of tangency, right? This chord in this outer ring is basically a tangent to this inner circle which your center of mass moves through. So basically, let's say that means what your normal forces are basically doing is it's actually acting as the combined normal force is actually causing your center of mass to move in a circle, right? To move in a circle, and it's causing also the center of mass to move in a circle. So basically, it's providing a centripetal force, right? So combined N is also providing a centripetal force. So what we can do by having these set of observations is we can reduce the problem to an equivalent problem, but we basically have let's say the same rod connected to a say massless rigid rod, and this has a mass m and a length L. Basically this moves in this circle which we already talked about of radius x, right? We'll figure out what the value of x has to be. But basically this is L by 2 and this was the radius r, so we can basically figure out x squared plus L squared by 4 is equals to r squared, right? So basically x is nothing but the square root of r squared minus L squared by 4, right? So basically now we have to figure out the motion of the bar in this configuration, right? So what are the forces acting here? So there's the gravitational force mg, and then there's a say tension force that's keeping it in the circle, right? This is the centripetal force, right? And so then there's also the component of this force, and we know that the component is mg sine theta, right? This is a basic problem. So basically, if I want to figure out the oscillations, it's basically this. We accept that this was the point C, which is the center of the circle. So the moment of inertia about the point C, theta double dot, should be equals to the torque, which is minus mg sine theta x, right? Which is the distance, which is the radius of this new circle. Now, since we're looking at small angles, so sine theta is going to be approximately theta, right? So we have IC theta double dot is equals to minus mg x theta, right? So basically, theta double dot is minus mg x divided by IC theta. This basically means that your frequency of oscillation omega squared is going to be mgx by IC. Let us see how to calculate IC. So IC is going to be that for a rod about the center of mass, ICM, plus that of that same rod which is shifted by a distance x, right? So I about the point x, right? So this is a standard result which will be ml squared by 12, and this will be mx squared. This is the application of the parallel axis theorem, right? So this gives you IC as ml squared by 12 plus n. We had figured out x was what, r squared minus L squared by 4, and actually if you carry out the computation, you see that IC has to be equal to ml squared by 6 r squared minus m squared by 6. Yeah. Let me write it here. So basically, IC will be equal to mr squared minus ml squared by 6. You can actually check with the computation, right? So now we had said that omega squared was mgx by ic, right? So if I were to write for omega squared, so omega squared was equals to mgx by ic, right? So we have mg, the value of x was r squared minus l squared by 4 to the power of 1/2, and here on the denominator we have m r squared minus l squared by 6, right? So now basically m's cancel and you can write it like so. If I take the square root on both sides, I get omega is equal to 6g by 6r squared minus l squared to the power of 1/2, r squared minus l squared by 4 to the power of 1/4. In fact, if we go back to our original statement that when L equals to 0, or when L approaches 0, basically expect the frequency to become that of a pendulum, right? So if we actually put L equals to 0 here in this expression, you will see that omega is equals to 6g by 6r squared minus 0 1/2 times r squared minus 0 to the power of 1/4. So basically your omega becomes equals to g by r squared square root multiplied by square root of r. So that means you just have g by r squared multiplied by r and r cancels, and you get g by square root of g by r. So here's the solution. So this was the solution. I hope you enjoyed.